By the end of the 1960s, containerization crossed the point where further progress was possible only as an industrial system. The experimental phase was over. Container transport required not isolated innovative ships, but a fleet capable of operating as a repeatable tool of global logistics. It is in this context that Sea-Land Venture must be understood. From the beginning, Sea-Land Service treated the container not as a single cargo unit, but as a component of a closed transport system linking ship, port, and inland transport. The container had to function equally effectively across the entire logistics chain. This approach demanded not only container standardization, but also the unification of the ships that carried them. Sea-Land Venture was built in 1970 at Bremervulkan in Bremen as part of the late second generation of container ships. It was not created as an experiment or prototype. It was designed as an element of a series for large-scale operation on international routes. Her sister vessel Sea-Land Economy belonged to the same series. Both ships shared the same hull architecture, hull geometry, and operating logic, allowing the operator to think of its fleet not around individual ships but around a type. Sea-Land Venture had a length of about 220 meters, beam about 29 meters, and deadweight around 23,800 tons. These parameters were at the upper end of the second generation but still within its structural limits. The superstructure was placed forward, a layout that preserved a long, continuous cargo space aft and supported more efficient container handling along the working deck. The ship used a steam turbine propulsion plant, still regarded as the standard for fast liner container services at that time. Her holds were designed as fully cellular with rigid cell guides. The cell geometry reflected second-generation practice and did not allow arbitrary stowage. The ship required containers that fit its matrix, ensuring repeatable operations and predictable results across different routes and ports. At the time of entry into service, Sea-Land Venture's capacity was not expressed in TEU. Documentation used container slot counts tied to Sea-Land's operating formats. Only later did unified comparison become possible. In retrospective conversion to ISO Series 1, her capacity is estimated at 1,200 to 1,300 TEU, typical for late second-generation tonnage. Sea-Land Venture and her sister vessels captured the moment when containerization became an industrial system. The ship ceased to be a unique object and became an interchangeable element of a fleet operating under a single logic. At the same time, such ships clearly outlined the limits of the second generation. Forward superstructures, steam turbine propulsion, and constrained potential for further capacity growth indicated that the next stage would require a rethink of container ship architecture itself. By the late 1960s, Europe approached containerization from a different starting point than the United States. In the US, container fleets formed around large private operators with their own integrated systems. In Europe, fragmentation was the defining condition. Different countries, ports, and shipping companies could not individually achieve the scale required for intercontinental container lines. The response was the creation of Overseas Containers Ltd, OCL, a consortium bringing together leading British and European shipping interests. Its goal was not experimentation, but the rapid creation of a full ocean container fleet capable of competing with American lines on equal terms. Within this logic emerged the Encounter Bay class, a series that became a distilled expression of second-generation container ship design in European form. Encounter Bay class ships were built at Hauelswerk Deutsche Werft in Hamburg in the late 1960s. They were designed as a series rather than as individual ships. The class included Encounter Bay, Jervis Bay, Flinders Bay, Botany Bay, and other sister units operating as part of a unified fleet. These ships had a length of about 213 to 215 meters, beam about 30.5 meters, and deadweight around 28 to 30,000 tons. This was the upper structural range of the second generation. The superstructure was placed aft, consistent with established European practice and reflecting the compromise between uninterrupted cargo holds and navigational demands. Propulsion consisted of steam turbines of roughly 32,000 horsepower, giving service speeds of about 21 to 22 knots. Speed mattered greatly. Intercontinental services had to run to fixed schedules synchronized with ports and rail hubs. The holds were fully cellular with complete cell guide systems. Cell geometry followed second-generation practice and left no room for non-standard solutions. The ship accepted only containers that fit the matrix, ensuring repeatable cargo operations and safety on long ocean passages. At the time of entry into service, Encounter Bay class capacity was not expressed in TEU. Documentation used slot counts tied to existing formats. Only later, after international standardization, did meaningful comparison become possible. In retrospective conversion to ISO Series 1, class capacity is estimated at 1,700 to 1,800 TEU, a practical maximum for the second generation while retaining aft superstructures, steam turbine propulsion, and limited deck stacking height. Encounter Bay and her sister vessels played for Europe the role American Lancer played for the US, but with a crucial difference. They were built from the start for consortium operation, where the ship had to function as a universal instrument for multiple participants. This is why emphasis lay not on experimental solutions but on reliability, repeatability, and scalability. At the same time, these ships clearly marked the limits of second-generation development. Further capacity increases required either major growth in dimensions or a change in layout. Steam turbine economics became an increasingly pressing issue. Encounter Bay became both the peak and the boundary of second-generation European container ship design. In the late 1960s, Japan entered the container era not as an experimenter but as a country already building an export-oriented industrial model. For Japanese shipping companies, containerization meant not simply a new cargo type but a transformation of maritime trade itself. Stable schedules, control of ship turnaround time, predictable port operations, and reduced losses at the interfaces between sea transport and inland modes. Within this logic, 1968 became Japan's entry point into the second-generation container world. Hakone Maru, introduced by Nippon Yusen Kaisha, NYK Line, became the first newly built Japanese container ship designed from the outset as a specialized vessel. Its importance lay not in a formal first label but in the fact that, in this project, the container was treated from the beginning as the basic operating unit rather than as one possible cargo type among others. Hakone Maru was built at a time when international container standardization was not yet complete and TEU was not used as a universal design unit. Capacity was defined by container positions for the actual formats used in the company's services. Only later, in retrospective conversion to ISO Series 1, Hakone Maru's capacity is estimated at about 750 TEU. This figure allows comparison with other second-generation container ships but does not represent how late 1960s design thinking expressed capacity. Hakone Maru became Japan's first practical step toward regular container operations on international routes. The ship did not aim at record size or speed. It consolidated the core principle. A container ship must be built around rigid geometry and operate within the discipline of scheduled liner service. In parallel with NYK, other Japanese operators began preparing their own container programs. In this context appeared Kazukawa Maru, associated with Kawasaki Kisen Kaisha, K-Line. Her emergence signaled that Japan's containerization was not confined to a single company, but was expanding across the national shipping structure. Even without detailed technical analysis, her appearance marks an important systemic fact. Containerization in Japan was becoming multi-operator and therefore irreversible. The further development of this trajectory can be clearly observed in Tohgo Maru. If Hakone Maru represented the engineering initiation of Japan's container era, Tohgo Maru demonstrates its confident maturation within the second generation. With a nominal capacity retrospectively estimated at approximately 1,170 containers and a service speed exceeding 26 knots, Tohgo Maru moved Japanese design firmly into the ocean-scale logic of the late 1960s and early 1970s. The ship reflects not experimentation but consolidation, increased capacity, higher speed, and clearer alignment with long-distance liner economics. Structurally, Tohgo Maru embodied the defining constructive logic of the second generation. The hull and hold spaces were organized around a fully cellular architecture in which container dimensions determined structural geometry. The ship was no longer adapting to cargo variability. Instead, cargo conformed to the ship's fixed internal grid. This inversion, where the container defined the vessel, was the fundamental architectural shift of the generation. By the time Tohgo Maru entered service, Japan was no longer merely testing container operations. It was scaling them. The transition from Hakone Maru to larger, faster, more capacity-oriented ships illustrates how quickly Japanese operators absorbed the new system and translated it into operational regularity. Japan's contribution to the second generation lay not in extreme dimensions or radical technical experiments, but in the speed, coherence, and industrial discipline of its transition. Hakone Maru marked the initial engineering commitment. The appearance of Kazukawa Maru showed the spread of container logic beyond a single operator. Tohgo Maru confirmed that Japan had fully integrated into the global container network at the structural level. By the end of the 1960s, the container industry reached a threshold beyond which further development without common rules became impossible. Second-generation container ships already operated on intercontinental routes. Fully cellular holds had become the dominant solution, and traffic volumes grew faster than the system's ability to reconcile different container formats. In effect, containerization had outrun its regulatory framework. The first 2 decades of containerization were marked by extreme diversity. Dozens of incompatible container systems existed. Under such conditions, global container service could not remain stable without efficiency losses. International standardization was not a theoretical initiative. It was a response to a technical reality already created by second-generation ships. Container ships with rigid hold geometry and cell guides had produced physical constraints that demanded alignment. Standards did not create the container from scratch. They formalized the practice already established at sea. The first key step came in January 1968 with ISO 668, which fixed basic terminology, external dimensions, and rated loads. It did not eliminate all length diversity, but it effectively recognized the 20-foot container as a base module around which second-generation hold geometry had already been built. In July 1968, ISO R 790 unified identification markings. The container received a standardized passport, understandable regardless of country of origin, critical for international liner services. A fundamental milestone followed in January 1970 with ISO R 1161, which standardized corner fittings. This step mechanically unified the container and the ship. Corner fittings became the universal contact point linking the container to cell guide structures, lashing systems, and port cranes. In October 1970, ISO R 1897 set minimum internal dimensions for general-purpose containers. This completed the basic cycle of standardization and created an aligned system in which container, ship, port, and inland transport operated within one geometric field. In parallel, the concept of TEU 20-foot equivalent unit gradually entered professional circulation. According to later maritime scholarship, the term is often attributed to shipping journalist Richard Gibney around 1969, although the original publication has not been conclusively identified. In practice, the expression 20-foot equivalent was already used descriptively in the late 1960s, while the abbreviation TU became more visible in the early 1970s and was clearly formalized in international institutional reports by the mid-1970s. At first, TEU served primarily as a comparative analytical tool. It allowed ships built around different container formats and operating systems to be evaluated within a common quantitative framework. Only in the early 1970s did TEU evolve into a full design and commercial metric, influencing ship planning, port statistics, and liner economics. It is essential to recognize that second-generation container ships were not designed for TEU. They were built around specific hull geometries, structural grids, and operational logics. Yet ships such as Encounter Bay, American Lancer, Sealand Venture, Hakone Maru, and Kazukawa Maru physically defined the scale at which TEU became the most workable common language for capacity. The metric did not precede the ships. Rather, it emerged from the practical need to compare vessels that already embodied a converging generational architecture. By the beginning of the 1970s, the second generation of container ships had fulfilled its historical role. It transformed the container from an experimental transport tool into a universal unit of global trade, prepared the fleet for ISO standards, and created the foundation for further growth in container transport. At the same time, the limits of this generation became clear. Aft superstructure layouts constrained effective hold length. Steam turbine plants delivered high speed at the cost of heavy fuel consumption. Deck stacking height remained limited by the era's structural solutions. These factors opened the way to the next stage, the third generation of container ships, designed from the start in a fully standardized environment and conceived in the language of TEU.